Okay, I'm just going to briefly talk about the difference between center of mass, that's physical quantity of interest, and expectation value, which is also something that's of real world interest that you can calculate using double integrals. Um, they show up in different contexts. They both show up in physics, actually. So this will show up in mechanics. So when you're dealing with physical objects, and just to give you an idea, let's say you're balancing some sort of plate or lamina on some sort of rod. So here's a rod, and then here's a lamina. Really, think of it as a plate. And if you put this at the center of mass, then does not fall, and then this thing will not fall, right? Because that's the sweet spot. The expectation value is a little different. It just tells you the average likelihood, uh, likelihood value of an interesting quantity. Uh, and we're working like in in the setting of probabilities, right? So, for example, if you have in quantum mechanics, for example, if you have a particle living in a box, uh, the average position, it won't be where you always find it, but it may be the most likely location or the average location. It's one way of quantifying the most likely location. So the difference is, aside from the physical context, is that the probability, the expectation value, you do not need to divide by an extra integral. I would say it's a little easier. So, in the sense that if I wanted to take the expectation value of x, well, this is the integral of x times your probability density over your region, and that's it. You're good to go. If you can do that integral, you're done. But if you want the center of mass, and if you want the x coordinate, then it's actually this. It's the same thing, x times your, I'm using rho, the Greek letter, rho of xy dA, but you actually have to multiply it by an extra thing. There's no x. So what that thing in the denominator represents is the total mass. So you have to divide this integral, and this integral here, it's called the moment. In x. So you divide the moment in x by the total mass. That gives you the center of mass. So really, there's kind of a connection between probability and the expectation value. The probability of the expectation value and the center of mass. So let me just write down the integrals again. If you can actually write it as this exact same thing. So I claim these are actually very similar things. Just to give you an indication why. And if I just put in that total mass and I stick it underneath rho, and I relabel as P, then we actually get the expectation value. So the only difference is that we replaced the mass density with a probability density. But this has actually no physical meaning. So it's why it looks more complicated. Because no respectable physicist or engineer would use a probability density in mechanics. It's just, you don't want to mix these two things up. You do not want to mix quantum mechanics and classical mechanics, for example. So we gotta just work with what we have. So let me just go over a heuristic reason of how to remember these, how to keep these two things apart. Dimensions. So it turns out probability densities, they have dimensions of 1 over the size of your region. So for example, 1 over meters squared, whereas mass density rho of xy, it'll actually have dimensions of mass, so mass divided by size. So it's not quite the same as a probability density. So for example, you could have kilogram divided by meter squared. And this goes for mass, this goes for, you could replace mass with charge, as long as you replace the dimensions here with charge. It'll be whatever you're interested in divided by size. And whereas probability density is always 1 divided by size. And so if you can keep those straight, then you'll have no problems. It's just an extra division step. Okay, thanks.